Hi, my name is Kunal, and this is the video walkthrough for questions 6.3 to 6.6. I just came back from the midterm review session. I apologize that we weren't able to cover this um, in the correct amount of time. So I'm just gonna try my best to really explain everything to make up. So yeah, so for 6.3, um, it's asking the worst case time to initialize an instance of weighted quick union with all the nodes being disconnected. So as you can see, there's like this table here that I found from the slides, which basically has like all the solutions, but I'm still going to go over and explain the logic behind it. So as you can see, the constructor is theta n. So I'm just going to explain why. So think about what does it mean that all the nodes are disconnected? Like you have n elements that are disconnected. It's no different from something like this, right? Like every single node is disconnected, and then we do that like n times. So think about like how like we would actually go about doing that. Like so if in our array, we're just gonna have an array, and in each element in the array, we're just gonna go and make the pointer to itself so that it's disconnected. So we're just gonna do that n times. So therefore, the worst case time is theta n. So I mean they're saying worst case time, but in reality, like theta n is gonna be the time it takes for like the best case time as well. Like it's always gonna take theta n. And with there was a question that came up in the review about why we're using theta and why not we're using O. You could technically use O as well, but usually for questions when they ask like worst case, best case, like when they specifically ask the worst case, you want to use theta. Otherwise, like if they say overall runtime, then you can use stuff like O and omega and stuff and theta. But in our case, like O of n, theta of n is the same because the best case is the same as the worst case. It's always going to be theta of n. So that's that. And then what's the worst case time to run connect on weighted quick union given n elements in the union? So let's think of an example to illustrate like why it's going to be theta log n. So I'm just gonna so like the worst case when we're doing connect is going to build a tree with like the maximum height possible. So let's just go about doing that. So let's say okay. So let's say like we have like I'm just going to skip a couple steps of the union just to like show you like the logic. But let's say we have like 0, 1, and then 2, 3. So I can see these two disjoint sets have like the same weights. So if we're going to connect on this, like you can choose either one. So in our case, we're just going to break ties by connecting the like the bigger one to like the bigger one numerically to the smaller one. So usually when you're connecting nodes, you want to connect the smaller tree in weight to the bigger tree. So for example, if this was like if there's like another like I don't know, I'm just gonna put something there. So if this was the case, then we definitely want to like connect this there. But because both of them have the same weight, we have to choose one. And in our case, we're just breaking the ties this way. So okay, so we're just gonna do this. Okay. All right. And now we have let's say like we have 4, 5, and then 6, 7. Okay. So we're not immediately connecting 4, 5 to this our bigger tree right here. And that's because we want to build like the tree with the most height as possible. So we want to connect these and then connect the trees. It'll make sense. So let's just connect. So we're gonna connect 4, 5, 6, 7. We're gonna choose the 4, 5 tree as the larger one. So it's gonna look like this. Okay. And then we want to connect both of these trees. And again, because they're the same weight, we just have to choose one. So we're going to choose this one. Sorry, we're going to choose this one as like the bigger one. So it's going to look something like this. Okay. So we're going to keep on doing that for like, and like we're going to keep on doing that n times. And like, as you like, and what you're going to see is that like if you have like the number of elements on one side and the height on one side, like let's just do a comparison. So like, okay, so when we have like just like one element, which is 0, the height is 0, right? Because like there is not connected to anything else. Okay, let's do 2 elements. 1, right? Because we're talking about like this case, it has a height of 1. Okay, so now let's look at 4. So like 1, 2, 3, 4. So now this has a height of 2, right? Because like you have, this is the first level, this is the first level, this is the second level. So it's gonna have a height of 2. So 4, 2. And then okay, let's do 8. So in our case, we have exactly 8 because like 0 to 7 and 0 counts as the first. So we have so how many like layers, or yeah, how many layers do we have? So we have like say we have 1, 2, 3. Okay, so we have 3 layers. Okay, so we can continue doing this, and we're gonna see that like for n layers, where it's always gonna be log n. Like think about it. What's log of 16? It's 4. Log of 8 is 3. This is log base 2. So yeah. So that's how we get our by analyzing this worst case, this is how we get our worst case of theta log n. Okay. Okay. Hi. So I realized that I may not have explained 6.4 that well. So I'm just gonna quickly clarify some things. So the reason that we were caring about the height when we were doing it is that because the function connect varies on the height of the tree. That's why like we looked at the height, and then the height was log n, so connect takes log n operations. And I'll just quickly go into why connect is dependent on the height. So let's say we have like this case, what we were doing before. So our worst case is going to be connect 0 and 7, because these are like the furthest apart, right? So, and to do connect 0, 7, what we want to do is we want to find like the parents of both the trees, and then like, you know, do the linkage. So okay, let's start with like 0. So 0 is already the root of this tree, so we're done here. Okay, and then for 7, we have to go to 6 and then go to 4. Okay, so like as you can see, like we're basically like to get to the parent, like the root of this tree, we're and from 7 we're basically doing like the height of the tree, and then we're doing the linkage. So like basically like doing the connect operation and finding the parents and all of that is proportional to the height of the tree. So that's why we try to like build like we try to build a tree. We try to grow the tree height really fast, and then the height that we find is our worst case. So yeah, hopefully that clarifies things up. Sorry, I forgot to clarify that. That's 6.4. Now 6.5. Okay, what's the worst time to run is connected on a way quick union given n elements? Okay, so let's just look back at our example, right? So let's take the case of finding is connect 7. Sorry, yeah, is connect for 7. So that's going to be the worst case, because as you see, when we check is connected 7, we're going to have to like, okay, we're going to have to traverse through 4, 6, and 7. Like we're going through these like 3 to find 7, and then that's how we know it's connected. So basically the worst case is also going to be log n, because as you can see, we're doing it like 1, 2, 3. Like we're basically doing it the number of times as the height of the tree. So and the worst case is always going to be like the max value, like, or like the furthest value away. So to find the furthest value away, like to find 7 in this case, we're going to have to do 3, like we'll have to go through like 3 elements, if that makes sense. So that's why it's also going to be theta log n. Okay. And now, okay, let's do 6.6. So 6.6 deals with path compression. So, okay, so we have like this tree right here with path compression, and we do find 8. Okay. So what find 8 does is find 8 like searches up the tree. So basically what find 8 is going to do is we're going to start here, and then it's going to go up to 7, 4, and then 1. What find 8 from my understanding is trying to do is just like find like the like what 8 is like connect to. It's going to try to go to the end. It's going to go all the way to the root, right? So basically what find 8 is going to it's going to return 1. So find 8 is going to return 1, right? And okay, and we see that like 7 and 4, like to get to 8 we have to go through like 4 and 7. Okay, so let's just keep that in mind. So I'm just going to write all these down. Okay, so what path compression is doing is like path compression is basically like shortening the path of like the path which you're doing in your tree. So for example, we want to get from like 1 to 8, right? So to get to 1 to 8, currently we have to go to 4, then 7, then 8. But what we want to do with path compression is just make it like immediate, right? And also keep in mind that like even to get to 7, we have to go through 4 and then to 7. And then even for 4, like, well, I mean 4 is already connected to 1, so it doesn't matter. So basically what we want to do is that we want to basically connect 7 and 8 to 1 directly, because it's kind of like shortening the path like which you need to traverse. So what your tree is going to end up looking like is let me just zoom in here. So it's going to be like 1, 2, and then 3, 5. This is basically same to before as before. And then we have 4, 6, and then we want to connect 7 directly to 1. So now 7 is going to be connected to 1, and then even 8 is going to be directly connected to 1. So this is what your tree is going to look like after doing path compression. So yeah, that's 6.3 to 6.6, and good luck on the midterm.